Today I'm going to be talking about how a small electromagnetic diaphragm pump works using fluid mechanics language and some quantitative estimates. So this device is an electromagnetically driven diaphragm air pump, which is a positive displacement compressor, which means that the pump generates flow by repeatedly changing the chamber volume. So when the volume in the chamber increases, pressure drops, drawing in air. And when the volume in the chamber decreases, the pressure rises and pushes air out, and it has one-way valves which allow this to happen. There are two main subsystems. The first is the drive unit, which is the magnetic coil and core assembly, which produces a time-varying magnetic force to oscillate the second part, which is the pump head, which is a flexible diaphragm which acts like a moving wall of the chamber, which has multiple holes in it to allow for flow. So the main flow path through this pump, there are two main functions. The first is the suction part, where the diaphragm moves back, increasing the chamber volume, which causes the chamber pressure to drop, opening the inlet check valve, and air can rush through into the chamber through 8 holes, almost like a jet-like inflow. Um, and then there's also the compression phase, where the diaphragm moves forward, decreasing the chamber volume, which increases the pressure. This closes the inlet valve and opens the outlet valve and allows the air to exit at a high pressure. So we made some sample calculations based off of what we measured from disassembling the pump. And we assumed that the density of air at room conditions is 1.2 kilograms per meters cubed. The dynamic viscosity is 1.8 times 10 to the negative fifth pascals. Gravity is 9.8 times, no, sorry, 9.8 meters per second squared. And the stroke is roughly 2 centimeters, as you can see measured here on the right. So the diaphragm area we measured to be around 1.2 times 10 to the negative third meters squared. And based on this, we found that the displaced volume per cycle was around 20.4 milliliters, um, which using this, we were able to find a rough volumetric flow rate depending on the frequency that which the pump oscillates. I'm assuming it would be more towards the lower end, around the 10 hertz, which would give you a 12.2 liters per minute. But depending on how well manufactured the pump was, it could also be up to 60 hertz, around the 73.4 liters per minute. Um, so the flow area of the 8 holes, we found that the area of each hole was about 1.26 times 10 to the negative fifth square meters, which since there's 8 of them, that gives us a area of around 1.1 times 10 to the negative fourth square meters, um, which when you calculate that into the velocity that is going through these holes, assuming it's at the lower frequency, it would be around 2.2 meters per second, but we estimated it could be all the way up to around 12 meters per second, depending on how fast the pump is oscillating. Um, Based on these speeds, we were able to calculate some possible Reynolds numbers within the pump. We estimated at 10 hertz it would be 540, at 30 hertz it would be around 1600, and at 60 hertz it would be around 3200. Um, The pressure drop, which we calculated in this pump, was relatively low due to a small area and it um, not being able to create as big of a pressure difference with air. But assuming that we had a bigger version of this pump, we gave it a rough pressure drop of around 10 kilopascals, which gave us a head of around 850 meters of air. And based on all of our previous assumptions, we were able to figure out that the power put into the fluid was 0.35 watts, which we could use to calculate the efficiency if we wanted to.